Okay, today's lecture is on stiffness method, and actually this lecture is from the sixth semester. I have taken from one of our teachers, but still I have managed to make my two questions as well. Okay, the stiffness method is it is based on kinematic indeterminacy, and I have given a lecture on static indeterminacy, and this is very basic. I mean, you must have studied it in your BSc. So I'm going to give you a very brief introduction of this stiffness method, and obviously we have to move on to 3D structures, and that is our prime objective. So I should not go into detail, but I should give you the basic concepts. For example, this is a beam, and you should know that this beam is overhanging beam because one of the um, portion is overhanged over a roller support. So in this case, for example, if I have to, and okay, again, if you have to find the kinematic indeterminacy of this structure, so it's very easy. Kinematic indeterminacy, as I have told you in the previous lecture, would be equal to 2j minus r. And joints, this is a joint, this is a joint, and this is a joint, and this is a joint as well. So there would be 4 joints in total. So 2 into 4 gives us 8 minus support reaction. So support reactions obviously one here and one here, one here and one here. So I've got 4 reactions in total. So I'll get 8 minus 4, and that would be support reactions of 4 and 1, 2, 3, 4 joint. So 4 degree. Okay. So it means this Ki is 4 degree, 1, 2, this and this, 4 degree. But I can reduce the Ki of this structure by converting this overhanging moment into applied moment. So it's very easy. That would be done in the next step. For example, this step. So you should know that, for example, this load forms a clockwise moment here. So this, as a result, resistive would be anti-clockwise because it's applying, it's making a clockwise moment. So as a result, the moment would be resistive, and that would be counterclockwise like this. And if I have to balance this, I have to apply it like this on this solar support. So this moment would be my applied moment. So as a whole, the structure would be converted into this structure. I mean, the basic determinate structure would be just like this. And the magnitude of this load is 10 kip, and this is 5 feet. So this applied moment, as I've explained here, 50 kip. So this would be the 50 kip foot moment, and that would be applied moment. Okay, you have selected these 2 degree of freedom, d1 and d2, and you should know that this applied moment 50 kip foot is supplementing d2. So this is d displacements, that d1 at this support and d2 at this support. These are action corresponding to these displacements. So for the first displacement d1, there is no action. However, for the second d2, that is second displacement or degree of freedom, I have this applied moment. And you should know that you have selected a clockwise moment here, and d2 applied moment is also clockwise, so this is plus 50. So this is the major advantage of this matrix analysis. The matrix analysis allows you to make as many as matrix as you can, and you are able to reduce the degree of freedom of a structure, as the original degree of freedom for this structure was 4, but I reduced it to 2 degrees. Okay, so I mean, all the steps have been explained, and this is very easy, so I'm not gonna go in detail. Okay, next step is, for example, you have find out the D matrix. Okay, D has been found out. Then the second matrix AD has been found out. The third matrix is ADL. Okay, now if I want to relate it to flexibility matrix, So in flexibility matrix, this is actually AR matrix, and this is actually DRS matrix, and this is DRL. So there is some way or somehow there is some symmetry, some correlations between two methods. So I am interested in finding ADL matrix, this ADL matrix, action due to load. And action due to load are actually fixed end moments. So based on the load given, you can actually convert, and your load given, I mean this is 2.5 kip foot and this is 40 kip. I convert it into fixed end moments. So this is 2 kip per foot, and the span of this span is 30 and this span is 20. Okay, this is 30 span. So 2 into 30 gives us 60. 2.5 into 30 gives us about 70, probably 30 into 2, 60, 75. Okay, and this is half. And the magnitude of this moment, you should know that this fixed end moment is WL square by 12. So you insert 2.5 here, the length is 30, and you divide it by 12, and you will get this fixed end moment to be 187.5 kip foot. I'm not interested here. I am interested here because these moments correspond to D1. Okay, for this span, 40-40, that is 20-20, and that can easily be converted into, and this moment, the magnitude of this moment is PL by 8. P is 40 and L is, I think, 20, and you divide by 8, you get 100 kip foot. So it's easy. It is written here. ADL1. ADL1 is action corresponding to action due to load, and that is corresponding to your chosen displacement. Action due to load corresponding to your chosen displacement. Here my D1 was, okay, let me first remove this. Now this D1, you should know that D1 is here, D1 exists here, and D2 exists here. So corresponding to D1, I have these two movements. This is clockwise, this is clockwise, these two are in the same direction. However, this is anti-clockwise. Here the net moment is clockwise, 187.5, and this is net 87.5, and this is clockwise, that is, it has the same direction as that of D1. Here it is clockwise, and obviously I chose D2 to be clockwise. So this would be my another matrix, ADL1 matrix. Why are they positive? Because they are in the direction of D1 and D2. Had you chosen D1 anti-clockwise, for example, if you had chosen D1 and D2 as in this direction, for example, D2 and D1, then in that case they would have been negative side here. But here it's positive. Okay, next I have to develop the stiffness matrix, and stiffness matrix is developed by applying the unit redundant actions one by one, and this is very basic. I'm not gonna go in detail, and this is very basic, but I'll okay. So in this case, for example, I have to fix all other supports. This is roller, okay, this doesn't matter, this is roller, okay, and I have to fix all other support, and I have to rotate it I have to give it a clockwise rotation. So clockwise in this case would be like this, because clockwise, and this is clockwise. So why this is clockwise? Because this is clockwise. Okay, the magnitude, because this is a near end, and this would be 4EI by L. Here D1 is equal to 1 and D2 is equal to 0, because this is D2 is equal to 0. So this would be 4EI by L. This would be clockwise as well. These would be clockwise. As a whole, the beam would rotate clockwise. So I mean, it has been shown here 2EI. The forend moments are 2EI by L. Okay, if this is clockwise, so you should know that you have to, I mean, it's good to understand the sign conventions. The sign, I mean, just consider this moment. This is a clockwise, So the load should be in which direction? The load should be here, like this, because it is applying an, if you rotate here towards this point, it forms an anti-clockwise movement and the resistive is applied, so it is okay. The direction here is okay. I have to balance this, so it would be balanced here like this. Okay, next consider this moment, for example, and you should know that I have to select the direction of this load. So if I apply it to be like this, upwards, so if you rotate it towards this point, it's forming a clockwise movement, and it is already a clockwise, so this is wrong. The resistive concept should come into account, so that's why I have to apply, make it here, it should be downwards. Now it is forming an anti-clockwise movement and resistive is applied. Next step is balance this with upward, and you should know that the magnitude of these loads are always 6 EI divided by L square, where EI would be depending upon the spans and L would be the length of these two, and they may differ because this is about 30 feet and this is 20 feet. So the value, however, the formula is same, 6 EI by L square. Similarly, 4 EI by L is near end moments and these are far end moments. Okay, in the next case, it has been explained you can see why it is 6 EI, and he has actually found out 6 EI by L square. In this case, 6 by L square, the moments 4 EI by L and 2 EI by L, everything has been found out in this. Here in the next step, I have to give this rotation. So the thing would be, things are like, make every other thing fixed and give it to the clockwise moment. So if it is a clockwise rotation, so this would be the clockwise as well. This would be 4 EI by L, this would be 2 EI by L, and the load here would be downwards, anti, and the clock is applied, 6 EI by L square. So it's very easy. So you can easily, it has been found out. The span is 20, probably this is 30 feet, so no need here, but it has been found out. So next step is, stiffness matrix has been developed. And how stiffness matrix was developed, for example, I am telling you about this. Here, for example, the stiffness matrix would be developed like this: D1 is equal to 1, D2 is equal to 1. Here, the second column would be made. The values for the second column will be attained using this. So you should know that this was your D1, right? So this would be S11, this is S12, this is S21, and this is S22. So the values for column 2 would be attained in this step. So here S12 would be equal to this 0.1 EI, and S12, what does S12 signifies? S12 signifies D1 due to D2 is equal to 1. Similarly, S2 signifies the action at point where D2 has been taken due to D2 is equal to 1, because here D2 is equal to 1 and D1 is equal to 0. So S22 would be this 0.2 EI. So it's very simple, and your basic BSc knowledge is would be counted, and it is very important. And again, you have done it. It's very easy. AM matrix and AMD. This is AMD, AML, your original matrix. These are the moments you have taken. You should know that these are the moments, these are the vertical reactions, these are the moment, these are the vertical reactions. So it has been chosen very wisely and very easily. For example, this. So I think this is gonna be you can call it AM1, AM2, and it depends upon you. AM3, AM4, member actions, AF, AM5. Okay, AMD matrix. Here AMD, that is corresponding to D1 is equal to 1. Okay, you should know that it should have two columns. D1 is equal to 1, and this column was attained when D2 was taken as 1. And finally you find out these things, and it's very easy. I've also done this, on frame. Okay, this is another question. This is my lecture, and this is very easy. I mean, same concepts have been used. Overhanging portion has been converted into a moment. This 30 into, you should know that it is applying a clockwise moment. 30 into 5, clock resistive would be anti-clockwise, and then here would be clock. So it has got the same direction as that of D2, and its magnitude is 150 kip foot. So that's why here is 150 kip foot has been inserted. Fix end moments, it's very easy. Next step is apply a unit displacement. It's very easy. I mean, you have to keep all of the fixed, like you have to keep all of the supports fixed like this, and apply a clockwise moment. So clockwise moment would be like this. This is clockwise, and you should know that its magnitude would be 4 EI by L, this would be 2 EI by L, these actions. Okay, again I'm going to explain the directions. It would be like this, anti-clockwise, and it's clock. It's good. Have to balance this, balance it with this. Now consider this is clockwise moment, so there should be load that forms an anti-clockwise moment. So resistive is clock, just balance it. 6 EI by L square, 6 EI by L square. It's very easy. I mean, I need not explain it. It's very easy. Stiffness method is very easy. Okay, you should know that when D1 is equal to 1, this is case when D1 is equal to 1, a displacement D1 has been given, a magnitude of unit rotation has been given at D1. So in this case you will attain S11 and S21. This S11 signifies the position at where D1 is originally taken, and this 1 signifies that D1 has been taken as a unit rotation. Similarly, S2 signifies the position where D2 has been taken, and obviously this is the position, and 1 is the action corresponding to D1 is equal to 1. So in this case you should know that S21 would be 0.133. Okay, S11 is summation of this and this. It means it's summation of this and this, because this is 4 EI by L as well. So it's very easy, and you should know that when D1 is equal to 1 was taken, this is D2 is equal to 1 was when taken. I mean, this is very, I mean, this column has been achieved or attained from this figure. 0.2, 0.2, 0.4, 0.4, 0.133, 0.133. So it's very easy. Finally, using this mathematical model, you can always find D value using this formula, S inverse AD minus ADL. And another mathematical model for member actions would be AM is equal to AML plus AMD into D. So these two mathematical models are very important. It's very easy. I mean, but you have to work. You have to recall your basic concepts, BSc, because we are going to solve it for higher structures that are 3D structures. Okay, this is another question, and this is frame this time. You should know that this overhanging portion can be converted into applied moment, and that would be coming in AD matrix. So you should know that it is forming a clockwise moment, so there would be resistive moment here, and you can balance it with a clockwise moment. The magnitude would be 20 into 5, so 100. So 100 would be here. Rest, this is very easy, and you should know that initially the Ki of this structure was 3J minus R. So joints are 1, 2, 3 and 4. Support reactions are 1, 2 and 3 here. Obviously 2 here, 5. So it comes out to be 7 degree. Okay, 7 degree means here it was 3. It was 3. So straight away it has been subtracted, because this member or this portion has been converted into overhanging. I mean, it has been converted into applied moment. Then you are left, okay, you can easily do it with using the inspection method as well. It's very easy. Like if you have a frame like this, and the frame is like this, so the Ki of free end would be like this. Here the Ki would be like no, okay, this is fixed or hinged. The Ki would be like this, and here I have no Ki. So straight away I have converted this overhanging portion into applied load or applied moment. So I am left with this portion. Okay, now Ki is, you should know that 3 equations are available in plane frame. You should know that: summation Fy, summation Fx, and summation Mz. That's why we have got 3 reactions, I mean 3 degree of freedoms here. Okay, and here I have got this moment, but you can actually ignore the axial deformation. For this beam, this is axial deformation. Axial deformations mean, for example, this is a beam, so its cross section is very thick and very resilient to this axial deformation, so you can ignore this. Similarly, this column, the axial deformation for this column is like this, and it is very resilient to this deformation, so you can actually ignore this. So I have got 2 degree of freedom, D1 and D2. So it has been happened here. So we have got D1 and D2 only. Rest it is easy. For fixed and load, this is WL. This is like ADL, or action due to load. And again, it's very easy to draw the figures. I mean, when you take D1 is equal to 1, I mean, you have to give a clockwise rotation to this point. So imagine it like this. I mean, is it a clockwise rotation? You can see that it is a clockwise rotation in this direction. Similarly, this is a clockwise direction. So the deformed shape would be like this. You can see this is a clockwise. This is also a clockwise. So deformed shape is like this, and again, this everything would be clockwise. Everything would be clockwise. You should know that this is 4EI by L. This is also 4EI by L. This is 2EI by L, and this would be 2EI by L. And corresponding reactions, if required, that are very easy. 6EI by L square. And this is attained for D1 is equal to 1. This is for D2 is equal to 1. So in this case, you should know that from this figure, you should know that this is D1 is equal to 1, right? And D2 is equal to 0. Now From this figure I'll get S11 and S21. Now S11 would be from, if this is D1, right, this is D1, so S11 would be summation of this 0.1 and this 0.33. That's why it is 0.433. And S21, that is the point where D2 has been taken, corresponding to D1 is equal to 1. It means this figure. So at this point D2 was taken and it's 0.05, so it is 0.05. Okay, in the next step, when you apply D2 is equal to 1, so this would be the case clockwise, 4EI by L and 2EI by L. So this would be your S22 and this would be your S12. So you should know that S12 should always be equal to S21 because it's identity matrix, and that's why S12 would be equal to S21. I mean, these two should always be equal. However, these two would be different. So finally, it's very easy. I mean, you can easily stiffness matrix. I want you to solve this on your own. So I mean, it would be practice for you. I think I haven't solved it, but it would be practice for you. So I hope you go back to your previous lectures, I mean, that were taught to you in your BSc. You should have got some notes, and these two notes are also available, and inshallah I hope that you will understand the basic concepts of stiffness method.